Welcome back, Calculus. This is going to be a video that kind of does maybe a complete example of how to think about a solid of revolution problem. For you students taking the AP exam, I want you to know solids of revolution are not going to be on that exam this year. I mean, normally they would be, but AP decided they weren't going to put any material on there that would have normally been taught after March, essentially. However, we're kind of in the situation where dual credit. We have a dual credit student as well, so the dual credit syllabus has to go on as usual. And I think it'd be worth your while to learn how to do this, regardless of whether or not it's going to be on an AP exam. This is pretty much standard Calc 1 material here. So let's begin here with how to think about a solid of revolution problem. Okay. Tedious, come on. All right, now listen. I'm going to write up here. This is actually, it's number 5 out of your assignment. Okay, and while your numbers may differ from mine, I think the region and the concept is going to be kind of the same. But what it says on mine, it says find the volume of the solid obtained by rotating the region bounded by the given curves around the specified line. And so the boundary curves are these. The first one is y equals 4 times e to the negative x. The next one is y equals 4. And the last one is x equals 2. Okay. So it says there's a region on a graph bounded by those 3 curves. Okay, I know 2 of them are lines, but we'll call them curves. The first thing always to do is to draw the region in question. Okay, and so I'm going to draw this on a coordinate plane here. And so the easy ones are x equals 2. Remember, x equals 2 is a vertical line. I'll make it dashed. So this is x equals 2. Y equals 4 is another easy one. Okay, that's horizontal line. So there are 2 of the boundary curves. And then 4 times e to the negative x is no big deal either, right? E to the negative x is an exponential that decreases because of the negative exponent effect. And the fact that there's a coefficient of 4 means that the y-intercept is going to be at 4. Because remember, e to the 0 would be 1, so 4 times that. So it's going to look about like this. It'll pass K. And it'll go down somewhere. I don't know where it'll cross, but it goes like that. Okay. Now, is this a perfect drawing? Well, you tell me. Obviously not. But the region of revolution here looks like that. I'm going to lightly shade the region bounded by those 3 curves. Okay, so we're going to revolve that region around a specified line. And the specified line is we're going to revolve this around the line y equals 8. Okay, now y equals 8, that's, let me make a little room here. That's up here. That's going to be y equals 8 right here. Okay. So essentially, if you want to think about this conceptually, we're going to be taking this region and we're going to be spinning it around that axis of revolution. And, it looks like it would create some sort of a ring, I suppose. There's a hole in the middle and, maybe it looks like one of those frisbees with a hole in the middle. Okay. Now, what's going to happen here is we are going to use the washer method, okay, to do this. If you want to think about a typical slice of that, okay, we always draw our slice. Listen here, because I haven't said this before. Draw your typical rectangle perpendicular to the axis of revolution. So since the axis of revolution is horizontal, I draw this vertically. Okay, I draw my slice of region. Remember, think about that rectangle. We're going to revolve that rectangle around the axis of revolution. And when I do that, can you take, okay, it's going to create a washer. And every single, little segment I draw in here, if I revolve it around the axis of revolution, is going to create a washer. We find the volume of a typical washer, and then we integrate to add up the washers, add up all the washers. Now, I think in the last video, discovered the washer formula, which is the volume is equal to pi times the integral from a to b of big R of x squared minus little r of x squared times dx. That washer formula works for solids revolution created by revolving a region around a horizontal axis. And remember, if you're going to revolve something around a vertical axis, these become r of y's, and that becomes a dy. Okay, now here is how to think about this. Okay, if you do this procedurally, you can't go wrong. The first thing I'm going to do is I am going to write out an expression for big R of x. Think of big R as the outer radius of a washer. Okay, so big R would go from your axis of revolution to the far boundary of your shaded region. So it goes from y equals 8 all the way to y equals 4 times e to the negative x. Okay. So to find the distance between the axis of revolution and the far boundary of the shaded region, you always take whatever is on top minus whatever is on the bottom. In this case, the axis of revolution is on top. The far boundary of the shaded region is on the bottom. So I'm going to take this y value minus this y value. So it's going to be, big R of x is going to be 8 minus 4 times e to the negative x. That's big R of x. Then I'm going to write out an expression for little r of x. Little r of x is the it's the smaller radius of the washer. It's the radius of the hole in the middle. So it's always going to be the distance from the axis of revolution to the closest boundary of the shaded region. We'll say that again. Little r of x. No, Teddy. No. I'm dead serious. Okay. It's always the distance from the axis of revolution. Let me start over. Sorry. Little r of x is always the distance from the axis of revolution to the closest boundary of the shaded region. So in this case, it's the distance from y equals 8 down to y equals 4. So that, remember, to find that distance, I take whatever's on top minus whatever is on bottom. So that's going to be 8 minus 4, or just plain old ordinary 4. So little r of x is just 4 in this case. Now, look how easy this is once I have big R and little r written out. Okay, all I have to do then, the thinking is done. All I have to do now, hey sweetheart, is substitute the expression for big R in where big R goes, and substitute the expression for little r in where little r goes. So I'd end up with, and maybe I'll erase what's at the top of this board, put my volume expression up there. So the volume of this solid of revolution is going to be pi times the integral. And I haven't talked about the limits of integration yet. Well, to get those, I look at my shaded region. My shaded region, I have to make rectangles, vertical rectangles that start here and go all the way to here. Okay, from the leftmost spot in my shaded region to the rightmost spot. So it looks like this shaded region, the leftmost boundary of it is at x equals 0. So my lower limit will be 0. My upper limit will be the rightmost edge of my shaded region, which will be at just the vertical line, x equals 2. So I'm integrating with respect to x, so my limits of integration are x values. And then I'm just going to, well, big R of x goes right here, so that's going to be 8 minus 4 times e to the negative x, quantity squared. Okay, so I've got this much of my volume expression done. Teddy, that puppet can't be in the video. End of story. No. And then I have a minus sign, and then I have little r, which is just 4, and that also has to, those little r of x also has to be squared. Then I put a dx. Now, let me tell you something. This can be just a calculator entry, depending on the problem. All right, that depends on the problem. In this case, it looks like I could evaluate that using a calculator or by hand. What's going to make that decision for us is whether or not we need the answer to be an exact value or a decimal approximation. Now, looking at the box here in this problem, it doesn't say anything about rounding to any certain decimal place, which means I'm going to have to evaluate this integral by hand. Okay, that's great. Now, I understand the thinking is done. We've accomplished the solid revolution problem. Now it's just a matter of doing some calculus and integrating this expression. So I'll erase this, and I suppose we can do this. It might take a little while. How are we doing time-wise there, boy?
About 12 minutes.
Okay. All right, we'll try. So the first thing I think I'd want to do is
I'm bored.
probably expand out that expression. So that's going to be, I'm going to have to FOIL that. That'll be 64 minus, minus 32 e to the negative x minus another 32 e to the negative x. I think 64 minus 64 e to the negative x. And then plus 16, I'm squaring that second term. And that'll be e, and I'll have to square the e to the negative x as well, so it'll be e to the negative 2x dx. Well, I forgot my minus 16 there. And I kind of wrote the dx on the slant there. Okay, so now we can just integrate term by term, I believe. One thing I notice is there I can at least factor a 16 out of all those. That'll just make my numbers a little bit easier to deal with. So I'm going to drop down the line and write this as 16 pi times the integral from 0 to 2.
You're at 13 minutes.
All right, thank you. So 64 minus 16, that's going to be 48. And then if I factor out a 16, that'll give me a 3. Then minus 4e to the negative x plus e to the negative 2x dx. Okay, so I did a couple of things there. If I did it too quickly, I combined those two like terms to make 48. Then I factored a 16 out of that, which made it become a 3. And then I also factored a 16 out of this term, and I factored a 16 out of that term. Okay, now it's time for some anti-differentiation. Well, okay. That's going to be, how are we doing today?
14 minutes.
All right, I tell you what, let's pause there. I'll finish this. I mean, you could finish it on your own, but I will come back and finish this in a subsequent video. Thanks for watching. Have a good day.